fellow delegates and invitees and other participants. It is my pleasure to announce that we are entering into the day 2 session. This session, a parallel session, technical session is the 10th, convened in Hall B, and we have Chair Dr. K.S. Nanjundarao from Indian Institute of Science, Bengaluru, and Co-Chair Dr. Snehalal Kaushik from GCIMT, Guwahati. It is my pleasure to introduce Dr. K.S. Nanjundarao, who is chairing the session on this occasion. Dr. K.S. Nanjundarao is currently the Chief Research Scientist in the Department of Civil Engineering, Indian Institute of Science, Bengaluru. He obtained his PhD degree from Department of Civil Engineering, Indian Institute of Science in 1995. He has extensive teaching, research, and consultancy experience in various domains of civil engineering. He has published more than 60 technical papers in peer-reviewed journals and conferences, has supervised research work of 20 students at University of Science, leading to doctoral and master degrees. He is a recipient of ACCE Nagadi Award in 2008 for Best Publication in Civil Engineering for the book titled Alternate Building Materials and Technologies. He has served as a member of Academic Council in National Institute of Engineering, Mysore. He is currently the chairman of Building Works Committee of Visvesvaraya Industrial and Technological Museum, Government of India, and Tender Committee of JNCASR, Bengaluru. This is the brief biodata, sir. On behalf of the organizing committee and on my behalf, I welcome you to chair this session and conduct the proceedings, sir.
Thank you, Professor Govindaraju.
And it is my pleasure to introduce our co-chair for this today's session, Dr. Snehalal Kaushik. Snehalal Kaushik is an assistant professor in the Department of Civil Engineering at Girjananda Chaudhary Institute of Management and Technology, Guwahati, a structural engineer and a PhD from I.I.T. Guwahati. She has research interests in earthquake-resistant design, nonlinear behavior, seismic retrofitting, and earthquake damage surveys. She was an active member of National Information Center of Earthquake Engineering at IIT Kanpur several years. She has published many research papers in national and international journals and conference proceedings in different sectors of the research areas. So with this brief biodata, I welcome Snehalal Kaushik to participate in the session as a co-chair. Now I will hand over the floor to the chair and then co-chair for this session. Sir, over to you.
Thank you, Professor Govindaraju. It's now what I would like to do is to share my responsibilities with my colleague, Dr. Snehal Kaushik. She will be managing the last 3 papers presentations, and I will be managing the initial presentations and the special lecture. And just for the sake of completeness, I would like to welcome you all to this session. A warm good morning to all of you who are in this hall of this conference. And in this session, we have one special lecture to be delivered by Professor Sireesh and 6 paper presentations. And the total time allotted is 120 minutes. And it is now my pleasant duty to introduce Dr. Sireesh. Dr. Sireesh is currently a professor at the Department of Civil Engineering, I.I.T. Hyderabad. He obtained his bachelor's degree in civil engineering from JNTU, Kakinada in the year 2000 and integrated PhD in the Faculty of Engineering from Indian Institute of Science, Bangalore in the year 2006. Before joining IIT Hyderabad in 2010, he was a postdoctoral research fellow cum lecturer at the University of Texas, Arlington, USA. His research interests are in the broad areas of pavement geotechnics, foundation engineering, soil stabilization, and numerical modeling of geosystems. He is active in teaching UG and PG students at IIT Hyderabad. Professor Sireesh has supervised doctoral research work of 5 students, and currently 5 more students are engaged in doctoral research under his guidance. Any updates Professor Sireesh can give? He has supervised several PG students in their project work Dr. Suresh has published more than 200 technical papers and reports in peer-reviewed journals, conferences at national and international level. Dr. Sireesh is conferred with several awards for his contributions. To name a few, he is the recipient of the Best Teacher Award for the years 2014 and 2018 at IIT Hyderabad. He is a recipient of DST Young Scientist Award in 2012. Dr. Sireesh is also a fellow and member of several professional bodies. Just to name a few, he is a life fellow member of Indian Geotechnical Society and IRC, Indian Road Congress, and member of American Society of Civil Engineers. He is on the editorial board of Indian Geotechnical Journal, Proceedings of ICE Ground Improvement Journal, Journal of Materials in Civil Engineering, ASCE. With this brief introduction, I now invite Professor Sireesh to deliver his special lecture titled Resilient Behavior of Stabilized Reclaimed Bases. Over to you, Professor Sireesh.
Thank you, Dr. Nanjendra. I mean, it was a very elaborate introduction. I thought it should be a brief one. Thank you so much for this opportunity to present some work that what I'm doing here at IIT Hyderabad. So let me talk about today's presentation topic. This is resilient behavior of stabilized reclaimed bases. So this is actually a project funded by DST, Technology System Development in 2015-16 timeframe. And we have completed this project already. And this is just outline because of paucity of time. So I'll just run through the introduction, necessity of the work and approach, and some results and design methodologies. So looking at the road network in India, we stand second in the world, longest road network in the world, very next to United States, with 5.9 million kilometers. And this pie chart shows us how distribution happen in India, like national highways versus state and expressways versus rural and other roads. So the point to be noted is like 95% of our roads are other roads which can carry a lot of traffic and more than 500 commercial vehicles per day. And the national highways are almost like 1,500 to 2,000 commercial vehicles per day. And most of our roads are flexible pavements, and generally the cross-section of pavements are shown here. And there are two different sections that are presented. It depends on the subgrade conditions. If subgrade is fairly better, the thickness of the base and subbase layers can be like minimized and for a given traffic. For the same traffic, if the subgrade is very weak, then we have to increase the layers or thickness of each layer to make sure that the stresses and strains going on to the subgrade will be minimal. Okay, so now let us look at quickly what is the market size and government initiatives in pavement industry or road construction or road infrastructure in India. Almost like Indian government, present government is actually allocated about 1.4 trillion US dollars to be spent on pavements and road construction for the fiscal year 2019 and 25. And National Highway Authority of India has targets towards 4,500 kilometers of road projects to be awarded. And almost like 1,300 kilometers of roads were already awarded in the first half of this year. So, and it is to be like almost 18% of capital expenditure for the year 2019 to 25. That means almost 20% of entire budget is spent on this road infrastructure. So just to name a few, like Honorable Prime Minister, Mr. Narendra Modi has announced recently Bharatmala Pariyojana project, which is almost like taking 5.3 lakh crores in Indian rupees to build almost like 83,000 kilometers of road in next 3-4 years. So then it's fine about all the projects and the vision plan for next 5 years. But what are the challenges that we face is approximately, when I calculate roughly, it is taking about 12,000 tons of natural aggregates to just build a 2-lane kilometer of a national highway. So all these 80,000 kilometers that I have just talked about, just I'll leave the math up to you to calculate how many tons of natural aggregates are required for this kind of construction in next couple of years. So that's a major challenge, and we are going to consume all their natural resources in building these roads. And if you look at northeastern states, the quality of rocks and quality of aggregates are very, very poor. And we definitely need an alternative secondary materials for that. And if you look at payment infrastructure on the other side, how the designs are going to take place, these are different payment distresses that I have noticed are pointed here. If you look at the pavement thicknesses of different layers here, and generally we find fatigue cracking on the asphalt layer, and also rutting, which is like a depression in the pavement surface. This is basically due to the vertical deformation or settlements of the subgrade. So if the subgrade is very weak, then we will see a lot of rutting along the wheel path of the on the road. And fatigue cracks are because of the tensile strain that is mobilized between the interface of asphalt layers and granular layer. So these two are major concerns, and the payments are designed based on these criteria. One is fatigue criteria and the other one is rutting criteria. Otherwise, also we see a lot of other problems like roughness, reflective cracking, and potholes. I'm not getting into these details, but the payments are designed generally for the first two. And if you look at the alternate materials to be used to meet the requirements of nation today, several potential alternative materials can be used, and those could include, but not limited to, building and construction waste, crumb rubber, fine glass aggregates, crushed bricks, and recycled concrete, and recycled asphalt pavements. So recycled asphalt pavement is the topic for today's presentation. And in short, we call it as RAP, reclaimed asphalt pavement. So reclaimed asphalt pavement is nothing but reclaiming the asphalt material or aggregate material from the pavement during its reconstruction or resurfacing or any highway expansion project. So generally, this RAP material contain aggregates and coated with asphalt on the surface. And if I extract all these asphalt out or bitumen out of this material, and we can see beautifully the good quality aggregates and good amount of filler material, which is necessary for the road construction, which are hidden in these particles. So these construction materials, if not properly used, we are actually throwing them in the landfills. So what we studied in this project is how to use this material back into the pavement construction. And it is not that easy to directly adopt this material, even though they are having a lot of good construction materials here, but because of the asphalt coating. So the behavior of the material or particles will be different if the coating is available on the surface. So the production, if you look at the production of RAP across the world, production is actually done based on 3 different methods: cold recycling, hot recycling, and full depth reclamation. I'm not getting into details, but in cold recycling, this is the picture taken very close to the I.I.T. Hyderabad campus on National Highway 65, where these kind of cold recycling millers or regen kind of equipment will be used to mill the top surface. And sometimes this top surface will be milled and actually thrown very next to the road, or otherwise sometimes we can carry and stockpile them as we see here. Okay, it is not a hillock, but it is like a stockpile of RAP material. So this RAP material, once it is stocked, then we can definitely use back into the payments, but there are different challenges that we'll talk about. So this is the amount of RAP or fly ash that I'll talk about in a minute, produced across the world. So if you look at the United States, they are about 110. These numbers are slightly older, 2 years older, but they would have reached 120 million tons per annum. That's the production rate of RAP material across in US. But India is about 4 million tons. When we started this kind of project in 2010, India was at very minimal. I mean, it's not in the graph to speak about. So, but as I mentioned earlier, India has the largest road network that very next to United States. That means the milling operations also would be should have been somewhere here, right? In between US and UK. But our milling operations are not that prominent or not encouraged yet. So we need to encourage that portion, and then we can definitely make use of the material back into the pavement construction. So this is another production of fly ash material across India. And this is from 1990 to 2030 projections. So we see that almost like 2,000 to 3,000 million metric tons of fly ash is produced in India, and the usage is slightly increased now. Is slightly older numbers, but majority of the fly ash is actually dumped in stockpiles and lagoons. And this is again environmental concern because of the air pollution and water pollution that is expected from these bottom ash and pond ash ponds. Okay, so how to use these two material together to make a green product is our challenge. So with that little background, these are the summary of objectives that I have created. So the main objective is to prepare a design mix for reclaimed fly ash stabilized reclaimed bases. In short, we call it as FRB mixes, and then to evaluate the resilient behavior of these materials, and then go with the design methodology. So to design them, basically I.I.Sc Indian Roads Congress has given a specific guideline in 2018, IRC 37, for a cement treated basis. Okay, it is not for fly ash treated basis, but there is a mention about cement treated natural aggregates. So similar data can be considered, or conditions can be considered to design these mixes with fly ash and RAP. So the code recommends that when CTBs are used in payments, it has to have unconfined compressive strength of 4.5 megapascal and resilient modulus of about 450 megapascal. This is our interest, because majority of these payment designs are based on the resilient modulus values, and that's the topic for today's discussion. And apart from these, durability studies have to be conducted, and the weight loss after 12 wet dry cycles should be less than 14%. If the material weight loss is more than 14%, that means the cement treatment or any stabilized material is not meeting the requirement. So they will not be considered for payment construction, because they can deteriorate before the end of the design life. So these are fatigue and rutting limiting strain equations, where resilient modulus of the particular subgrade layer is considered. And here is the tensile strain, and this is vertical strain, and NF are limiting life cycles or service life of the payment. So this is the methodology that we have adopted. Basically, we have collected material, and then preliminary design was conducted. Performance checks was done. Then once the material is behaving perfectly fine for the limitations that we have, design approach was proposed, and field study was also conducted. So these are material properties. Because of shortage of time, I'm running through these. And X-ray fluorescence data was collected. Tests were conducted on different fly ashes. We have almost 4 fly ashes tested, including one from Queensland, which is in Australia, and 3 from Andhra and Telangana states of India. And except Neyveli fly ash, most of these fly ashes are class F fly ash. Neyveli fly ash with higher calcium oxide content is class C fly ash. So each fly ash with different combinations of silica, alumina, ferrous oxide will behave differently, and we need to find what is the optimum combination for a road mixture. So in this case, what we have considered is 60% RAP material was added to 40% natural aggregates or virgin aggregates, and fly ash was added as a binder and a stabilizer, about 20%. And to activate fly ash, because they are all classified as class C fly ashes, so liquid alkali activator, which is nothing but alkaline solution, is required to energize or activate these inert silica and alumina from the fly ash. So sodium hydroxide and sodium silicate was added in a combination of different combinations. We'll be talking about 50-50% and 70-30% here. So these are compaction characteristics to prepare the specimens for resilient modulus and UCS testing. So let us look at what is resilient modulus of these resilient RAP mixes. So just to give you an idea, what is the concept of resilient modulus? For example, if this is the payment structure, and this is the base of base layers and subgrade here. So because we are talking about resilient modulus of base sub base layers, which is going to be like a stabilized RAP material. So for example, if you consider a small elemental area or volume here, and vehicle is somewhere very far from the structure, point of observation. So this is the point of reference for us, and with the vehicle very far from the point of observations. And the stress conditions are very nominal, and this is because of the dead weight or surcharge or even overburden pressure on that particular point of observation. So then when there will be a vertical and horizontal stress. And this is a pressure distribution diagram I have just considered as a 2:1 pressure distribution here. When the vehicle approaches this point of reference, then what happens, there is still a pressure distribution which will not be directly influencing it, but there is a small vertical deformation or vertical stress that they can increase. And when the vehicle is exactly on the point of reference, then there will be a huge amount of vertical pressure, and there will be the stress ratio or stress concentration on this element will be much higher. And when you consider just about the point of approach, when the vehicle approaches the point of observation, then there is another stress condition that we can consider. So always you can take coefficient of pressure at rest to consider what is a confining pressure which is available. So when vehicle is traveling or traffic is allowed on the pavement surface, then the the layers will actually subjected to various vertical and which will be like deviatric stresses and confining stresses. So based on these combinations, and this is not only one tire here, the wheel that we are talking about, there are different classes of vehicles that we have, including from cycle to 18-wheel truck trailer, right? So the weights and loads coming onto this point of observation here would be entirely different when there is a different combination of vehicles that are passing on this pavement. So each combination will have a certain weight and stress conditions on this element. So based on that, 5 combinations of confining stresses and 3 combinations of deviatric stresses are considered on the element, and that gives us 15 combinations. And each combination of the stress, like one confining pressure, one deviatric stress, will be applied for 100 cycles, and the series will continue. And this is a small animation. This is actually done as per ASTO design guideline. And if you look at the specimen here, and the strain that is accumulated here can be seen in this picture. And if you look at the characteristic curves that we can plot, this is a resilient strain, and this is accumulated plastic strain. Plastic strain is nothing but rutting on the pavement surface. And now resilient modulus is defined based on the sigma D, and sigma D is nothing but cyclic deviatric stress, which is the cyclic loading applied on the pavement surface, and recoverable strain, which is obtained from each cycle. So a resilient modulus is actually measured for the last 5 cycles, that is out of 100 cycles, and an average value is reported as a resilient modulus. So a sophisticated cyclic triaxial or repeated load triaxial apparatus can be used here. This is at IIT Hyderabad to conduct resilient modulus testing, and this is a sample preparation for that. And now you can see the effect of cyclic deviatric stress on resilient modulus for different combinations of confining pressures for different fly ashes, which are stabilized for 28 days. And you can see that with increase in confining pressure and deviatric stress, the resilient modulus increases, because the recoverable strain, total strain that we have seen in the previous figure, here, can be reduced with increase in the confining stress and deviatric stress. So that's why the elastic strain also will come down. That's why the resilient modulus is increasing, because the denominator is reducing. Okay, so this is average resilient modulus for a short and long term. And these are base and subbase layers. Now we can see that.
Sorry.
Yeah, this is the baseline as per IRC, and we are looking at almost 1200 megapascals, but the requirement is only 4 megapascals.
Please, sir, it will be my.
Yeah. So here, unconfined compressive strength tests were also conducted in similar lines, and we have tested up to 270 days strength, so that we can see that how the strength is developing. So you can see that unconfined compressive strength is like a characteristic compressive strength of concrete, and it is about 18 megapascal. So it is nothing but, I would say, that we are preparing like a concrete layer, lean concrete with M18 or M10 or M15 here, with the least value that we have considered, then it is the strength of the concrete that we are producing out of recycled or reclaimed asphalt pavement and fly ash itself. So this is one important graph that shows how the strength is developing with respect to the ultimate value. Ultimate value here is considered as 270 days, but 7 days and 28 days are having about 12% strength at 7 days, and it is achieving the concrete is achieving about 40% at 28 days. That means this information is very useful for the field engineers, because right after construction, what is the strength they are expecting, and based on that, they will go for the next layer construction, or even moving the construction equipment on these layers. So up to 7 days is actually a minimum period that we don't want to disturb the layer, so that it will achieve at least 10 to 15% of the strength, ultimate strength. So at 28 days, obviously 40% strength is attained. It is very different from regular concrete or Portland cement concrete, because at 90% of the strength is expected at 28 days, but here it's only 28%. So with these important data, I'm not showing other extensive studies that we have conducted, just to give a brief idea about how the pavement design can be taken up with these recycled materials. So this is actually a framework that we have created, which is called semi-mechanistic approach, because if you look at ASTO's design guideline, it is mechanistic empirical, because empirical equations are also generally used in these pavement designs. So we wanted to reduce that by taking more of mechanistic parameters, which is like resilient modulus, shear strength, and other properties, and also considering the climatic conditions like durability and leaching effects and other environmental factors to propose the design here. So this is a typical cross-section of the material of the new construction process that we have introduced. So here a drainage layer is provided above the moderately stabilized RAP basis, because drainage will not be very high when the material is stabilized with any stabilizer. Right. So these are different variables that we have used. I'm not going into detail here, but this is a graph that shows how base layer resilient modulus of the RAP material with layer coefficients here. And we did not propose one single unique curve here, because the pavement design or pavement thickness of each layer will completely depend on the CBR value. If the subgrade is very poor, we cannot have one size fits for all kind of design here. That is the case earlier. I mean, when you talk about ASTO design methodology, it is only one single equation that gives the pavement construction. Designs for single equation was proposed earlier. So here we have proposed 3 different equations to cater for with high coefficient of determination. And with this new design methodology, we developed design charts based on resilient modulus of the base of base layers, and thickness of these layers can be directly read from this particular graph for different CBR conditions. So we have taken this data and with the confidence we went and constructed field sections. This is the original design conducted, developed by Andhra Pradesh Road Development Corporation. And the traffic was about 20.3 million standard axles, cyclic loading, and the thickness was about 530 millimeters. So we have redesigned the same section using our present design and methodology, and we can actually provide, instead of 550, the base layer itself, we reduce from 250 to 175 millimeters. A reduction of 20% material can be reduced from this approach. So these are some construction pictures that we have adopted. This is the road with base layer, and this is the curing for seven days, and rolling was done. And some instrumentation like inclometers and pressure sensors were adopted. And after construction of all the other layers, including the surface layer, inclometers were monitored with traffic. This is obviously we have asked them to stop here, But generally, this data is collected throughout this length of the road when the traffic is moving. And we will know like what are the different vertical deformations and settlements across the pavement layers. And this is our horizontal in kilometer data from control section. And we monitored for almost 3.5 years. And this is the control section. And if you look at the vertical axis, they are about 10 millimeters here. Okay. And the data is, and the deformations are about 2 millimeters plus or minus. Here it is 4 millimeters in the control section. So what we can conclude from here is that the recycled base material is performing either better or equal to the conventional design with a reduction of about 20% of thickness. So that's the key factor or key finding from this study. And this is the road condition of the road after 3.5 years of monitoring. And this is a stretch of 250 meters that we have laid using that. And this part is a conventional road. The other side of the road is made from the FRB road. So with that, I would like to conclude that a high volume of RAP, about 60 to 70% of RAP can be used. That means 70% of virgin aggregates can be reduced here. And fly ash is another good stabilizer, which can help us as a filler cum stabilizer. But a proper treatment or alkali activator is required. And resilient modulus of RAP material can be improved with fly ash stabilization. And the MR values or resilient modulus values of stabilized RAP is found about 1400 to 1600 megapascal. But the requirement for as per IRC is about only 450 megapascal. So a semi-mechanistic design approach was proposed in this study based on resilient modulus. And 25% of reduction in pavement base material and 20% reduction in cost was achieved at the end of the construction and 3 years of design life. So hence RAP is a sustainable material which can be adopted for pavement construction. And coming to the acknowledgements, I would like to acknowledge my PhD and master students at IIT Hyderabad, especially Deepthi and Mahesh, who extensively worked on this project, and Mr. Sharad, who was a master student. And I'd like to thank Department of Science and Technology for funding this project, and APRDC for letting us construct the road in the on a state highway. And also like to thank all the organizers for providing me this opportunity to present my work here. And this is my my group at IIT Hyderabad. And thank you very much for your attention and patient hearing. If you have any questions, I'm more than happy to address. Thank you so much.
Thank you, Professor Sireesh, for a very nice presentation.
Thank you.
I just would like to see, Govindraju, are there anything posted on Q&A in the Q&A box? I don't see anything here.
No, sir.
No.
Yeah. Again, Professor Sireesh, thank you very much for a very nice presentation. However, I would like to just make some comments and seek some clarifications from you. So you said that you are using fly ash and the alkali as an activator. So this is similar to our geopolymer kind of thing.
This is geopolymer, yes.
Alkali activated kind of thing.
Correct. Yeah. It's a geopolymer, yeah.
Yeah. So the sodium hydroxide solution, what you're using, what is the molarity of the solution?
Yeah, we have used different molarities because we have used 4 different combinations fly ashes. So it varied anywhere between 0.5 molar to 3 molar. Highest is 3 molar for Vijayawada fly ash. And when compared to concrete, this is very less. In concrete, generally you use 6 to 8% of molarity, 8 molarity. But this is very low.
Normally we use. Is there any reason for using such a lower molarity in road construction?
Because the target values are very limited. Target values are UCS and resilient modulus, and we don't want to dump chemicals into the road and spoil the environment also. So we have initially tested all the combinations, like different combinations with up to 0.5 molar to 10 molar. And we have seen like basically what we need is alkali environment, which is something like pH of 12.3. So that's good enough for us to activate the fly ash like silica and alumina, which are in inert state. So that's why we were good with this, and we have tried resilient modulus and shear strength as well, and those limits are much beyond what we actually require. So we are looking at only 4.5 megapascal and 450 megapascal. So those are very well satisfied with these combinations. So that's why we reduce the usage of like alkali activator in this.
Yeah, but the sodium silicate, is it necessary here? If the fly ash is quite good, then...
because fly ash is all, except Neyveli, in India, most of the fly ashes are class F fly ash, which has very low silica content, calcium oxide content, about 1 to 2%. And so they cannot directly participate in CSH or CAH gels. So what we have looked at is NASH gels, like sodium calcium aluminate silicates. So for that, for that combination, we have used, because these are like low calcium fly ashes, we have to reset on that geopolymer combination.
Did you try anything with the hybrid like GGBS?
Yeah, that's another combination. Fly ash and GGBS can be used because their silica and alumina are very highly reactive. Yeah. So what has happened in this case, this low calcium fly ash that we have used, the silica content which is available is not in amorphous state. Most of it is like crystalline. So very limited amount of silica was ready to react. So we need to supplement silicates using, water glass or like sodium silicate. So that was the reason why we have to add a combination. And if you look at Neyveli, which the combination of silicates and sodium silicate and sodium hydroxide, the ratio is entirely different. So somewhere it can be like 1:1, sometimes it is 1.5:1, something like that. So we need to justify or a priori, like we need to test it and see which combination is providing more, releasing more reactive silica. And then if more reactive silica is available, then we can reduce silicates in that supplement of silicates. Yeah. That way we have studied.
Yeah, it's a very good work, I would say, very appropriate and timely with the initiative of the government in trying to expand our roads.
Correct.
And also it's a very good thing that you are suggesting some things where you can use alternative materials rather than explore our natural materials, which is already so scarce, and we are making our countryside look bald and things like that. Anyway, I and you can't avoid getting bald, but at least our natural things has to be taken care of. So it's a very nice thing. And if anybody else has any comments, I would.
I want one clarification from Professor Sireesh. Professor Sireesh, it is a very interesting and highly informative lecture. I enjoyed a lot. But all said and done, you have a very good control in the laboratory for the mix design and achieving the target strength and all. But when it comes to the field study implementation level, how do you control all these mixes in certain
that's a very good question. Actually, out of this project, after 3 years, we have already constructed the test section, and the experience is entirely different. It's like a flip side of the coin. Like in the lab, you have everything is under control, but in the field, absolutely right. I'm with you. So there, to do that, actually, we need a lot of pre-preparation for the entire construction. So that took us like almost 3-4 days. And this sodium silicate and sodium hydroxide combination is also exothermic, and we need to just cannot dump the material there. So some pictures I've shown, but I could not get into the details because of time. So actually, we need to prepare the mixture a day before. At least this combination, like sodium silicate and sodium hydroxide combination, we need to prepare them, and but should not mix it with the fly ash and other aggregates. That goes next day. And we need to do this thing VRs, like that means like a late evening, late night, where temperatures are low, because it will produce a lot of temperature exothermic reactions, right? So because it is only 250-meter stretch, we could manually do it. But what I've recommended to DST or even to the government is that we can actually take batching plans for that. For example, if it is like for a couple of kilometers, we can adopt batching plans, and that their control can be like much better. So true.
Thank you very much.
Thank you, sir. Thank you very much for the opportunity, and I really enjoyed the lecture.
Sir, I have a query regarding this. Can we apply this thing on this bridge deck also? Like there also where roads are getting damaged because daily we need to repair and also.
Because
or you can suggest something. You can suggest something for that type of construction also over the bridge.
Yeah, I think Professor Ranjendra is right person to answer that. But anyway, let me try. Because it is not fully concrete. Or for example, if I look at the bridge deck, just to avoid two things. One is noise as well as damage to the bridge deck. Generally, asphalt layers are placed instead of again concrete layer on top of bridge deck. So in that perspective, I would not recommend this material there because it is low grade again concrete, and you need to wait for some time, and then mixing process is entirely different. And the stretch that you're looking at maybe 1 or 2 kilometers length. I mean, even if you look at large major bridges, right? So there will be other challenges other than just laying a road there. So in that case, I think always a good grade, there are multiple mixed designs are available these days in terms of asphalt layers, like crumb rubber modified or polymer modified or high grade viscous grade asphalt layers. Those can be provided, and that will also act as a cushion as well as noise barrier for the bridge decks. So yeah, my call will be like that. Probably
thank you. Yeah, thank you so much.
Professor Nanjendra can add maybe.
Sure. We will not save significantly materials in bridges. This is where the saving is more important, and that is the primary objective. Yeah.
Correct.
So if there are no more, and I think we will move to the next paper presentations, and let us thank Sireesh, even though we are at a distance. Thank you, Professor Suresh.